That's fine. That's fine. But I'm also okay if you don't really have to work with time.
Depends on how much support in this.
Sure. I mean, I'm fine. I mean, I'm just saying, right? Don't worry about it. Okay. That's it.
Okay, we will start the meeting in 2 minutes. Beforehand, now we would like to look for the 2 volunteer for note taker and 1 volunteer for Java scribbler. If you are interested in volunteer, please let me know. Raise your hand. Anyone? Okay. Okay. Shall I start? Okay. Let's start the meeting. Welcome. This is TCP Maintenance and Minor Extension Working Group. So my name is Yoshi, one of the co-chair of this working group. So before we start the meeting, we need 2 note takers and 1 Java scribbler. So if you could volunteer one of them, that would be really good. Anyone? Jana, how about you? No taker. Yeah, it's okay. Huh? Okay. Anyone volunteer? Oh, you can take one. Thank you. 1 more person. Bob, you don't mind? Not taking. No. Jana already volunteered, so you will be second note taker. No?
I probably not. Yeah.
Okay. 1 more person. Future will present. Anyone? And also JavaScript if possible. JavaScript are relatively easy. You just watch the Java room, and if someone make a comment on Java, go to the mic and then make a comment. Okay, thank you. Okay. So, okay, let's start with 1 note taker. Okay, and just a reminder, so when you make a comment or questions, please go to the mic and then speak your name before you make a comment or a question. That's the rule. And then also, when you submit your individual draft, please include TCPM in your draft name so that the chairs can keep track of the situation of your draft. And also, please don't forget about blue sheet. Please write down your name. Okay, and this is not well, usual one, so please keep this in your mind. And then this is the agenda for today's meeting. So we are starting from agenda busing and then working group status update. And then we have one presentation for working group items. Yujin will talk about LAC draft. And then we have several non-working group items. First one is generalized ECN from Marcel. And then next one is TCPM ECN improvement from Jennifer. And then third one is TCP option for low latency, maximum arc delay, and microsecond timestamp. This is from Neil. And then after this, Michael will talk about 2140 BIS draft. And if time permits, Yoshi will talk about max win draft. So any question about the agenda, comments or agenda? Okay, move on. Okay, move on.
Somebody on mute.
Oh, but no participant speaking. And so Marcus is ready for his presentation. So he's basically remote speaker of the ECN improvement draft. So Jennifer mainly talk about it, but no, if she cannot answer the question, he try to answer from the remote. That's the plan. Okay, so, okay, we have some update in working group chairs. Unfortunately, Pashi decided to step down from working group chairs. So he has worked as a working group chair for about 5 years. So I really appreciate his dedication, contribution, effort. He personally helped me a lot during working group meeting organization. And so I really appreciate him. And this is sad news, but fortunately, Michael Tuxon agreed with us to be a new co-chair of TCPM working group. So I think I don't need to introduce him to this community because I know everyone already knows his name and everyone knows how good he is. So I don't think I don't have to say much about this one. I just say 3 of us try to work hard to provide a good community, to good service to the community, and then we will appreciate your cooperation. That's about it. Okay, now move on. So we have several updates of the documents. So we have several working group items right now. So first one is EDO draft. And then according to the authors, they are still working on it. So they are mainly working on the continuing implementation and testing. The implementation is Linux based. And then right now they're checking interaction between TSO, LRO, GRO stuff. So I hope, eventually they will come back with some result, how to interact EDO and TSO, LRO stuff. But still, we are waiting. And the next working group item is 793 BIS. As you might know, this draft takes a lot of time, lots of painstaking task. But although progress is not that speedy, but we can see progress from time to time. We see some message from Wes sometimes on the mailing list. So although it takes time, it's keep progressing. That's all I can say so far. And then next one is cubic draft. And this is also work is ongoing. And according to authors, the new version will be submitted very soon, around the end of this month. So any questions so far? Okay, the next working group. Next working group item is TCP draft. And this is also work is ongoing. Then as you might notice, new version was submitted today. And then this draft, this version is basically addressed to several comments on the previous version. And then Chair is currently thinking this draft is getting mature these days. So maybe after we check this draft, maybe it's time to think about doing working group last call. But we still haven't decided yet, but now we are thinking it's close to working group last call. And then next working group item is RTO consider. So we have several feedback in the previous meeting in Germany. And unfortunately, I don't see much progress on this draft after the Berlin meeting. The problem is we cannot communicate the authors very well. And so right now, what we are thinking is now it's time to think about having an editor to this draft, and then so that we can address the feedback in the Berlin meeting. That's what we are thinking right now, but we still need to little bit discuss. Maybe during this meeting, I might want to discuss with media about this one. So that's the status. Any comments? Okay. Okay. And the next one is accurate ECN. And okay, media, please.
Yeah, so there has been a lot of discussion in the background on this draft, and there has been changes in the draft, and we're progressing. But I guess the message is, if you're interested in this draft, you have some contribution, there's an opportunity to become a co-author on the draft if you want to help. So let us know, I guess, right?
Okay. Which this one you are talking about accurate ECN?
No, the previous one. Sorry, the RTO considerations.
Okay, I see. And then next one is accurate ECN. And then new version has been submitted about a week ago. And then the author is asking a feedback. And then once we got lots of feedback, I think we can think this is draft is already matured to working group last call. But please provide the feedback to the draft. And then last working item is rack draft. We will have a presentation in this meeting from Eugene. So I think I don't have to mention about this draft very much. Let's discuss. Okay, this is the end of working group items. Any question, comments? Okay. And then with regard to non-working group documents, I already asked you guys to pay attention to one individual draft. So this is alternative backup ECN draft. And we have discussed this draft for a while. And then we right now thinking that this draft is getting matured. And especially in the last meeting in Berlin, we got some positive feedback on this draft as far as we remember. So I think rough consensus in the room in the previous meeting was kind of conditional accept. If the David's ECN draft is accepted at TSBWG, this draft might be ready for call for adoption, if I understand the situation correctly. So, but unfortunately, we don't have a TSBWG meeting right now yet. So once David's draft has been accepted, we might think about the call for adoption on this draft on the mailing list. and David want to make some comments.
David Black, author of the Scene Experimentation Draft. Yes, we're going to talk about this at THCWG tomorrow. I just uploaded slides. The intent is going to be to ask for adoption tomorrow of that draft and to be confirmed on the list so that this draft, I think there's at least one other you have here, can move forward.
Thank you. Any other comments? Okay, looks good. So now Chair's presentation has finished. Now move on to the individual presentation. Yu-Chun.
Hi everyone, I'm Yu Chon. I'm here to present the RAC draft. This is the first time it's just become a working group item. And this is done with my co-workers Neil Carwell and Nandita Dukipati from Google. Please, next slide. Yeah. So what is RAC? The key idea here is to really look at the loss based on time instead of counting dewbacks, for example, or counting some sort of other type of packets. And the right graph, actually left graph, shows how the flow, packet flow works for RAC. Let's say you perform a SYNAC and perform a handshake, and then you send two packets, P1 and P2, right? And then you get a sack of P2 instead of get an ACK of P1. So you know something has been, P2 has been delivered out of order, and usually that sack of P2 is a dewback. Right, and the conventional approach is say, well, let me wait for another two more before I start repair some packets. But as you can see, if you only send two packets and then you lost one, there is no way you can get three. So there are variants to say, let's wait just one dewback. But here the insight in RAC is really, if you get an ACK of P2, then you would expect P1 has arrived. And if not, it could be reordered. And so what you do is you wait for, say, a quarter of RTT. And if still you didn't get any acknowledgement of the P1 packet, then you simply retransmit P1 and then you get an ACK of it. And that's just sort of the essence of RAC in a simplistic form. You can think of that as simple as whenever you send a packet, you put a timer on it virtually. And as you continue to get ACKs, then you get a sense of, okay, some packets have arrived, but some packets have not, and you get some RTT measurement. So every time you get an RTT measurement, you refresh all these timers that for the packet that you haven't been acknowledged. And then if that timers exceed, the packet has been there for a certain time over an RTT or two RTT, then you can claim that packet is lost and you retransmit. That's the simple idea. Next slide, please. So the major addition to this draft this time, as it becomes a working group item, is that we include this old draft called tail loss probe, a TLP. And what TLP trying to address is essentially tail drops, which is really common for request response traffic. And drop tail today, drop tail queues are still very, very common. And at least on Google, for all the web transactions, we see a lot of tail losses. And today, the only way to repair a tail loss is through timeouts, because you don't get any ACKs. Everything after, let's say you send 3 packets in the example, and the first packet gets delivered, but the last 2 packets get dropped. And there is really no way you can recover it without a timeout. So what TLP do is very simple, is that after you get the ACK of the first packet, as the left-hand graph shows, then you wait for at most up to 2 RTT. Then you say something is wrong, and then we send a probe packet, right, like a scout, to see what's going on. So if that probe packet actually triggers an ACK back, then you know that at least 3 RTT has passed, and you can simply just use RAC's idea to say, well, look, P1 and P2 have not been acknowledged after 3 RTT. and it has even been have not even come back after I have sent a subsequent sort of a probe packet. So it's very likely the two packets really have lost. And then you simply start retransmitting the whatever packet that you're using are lost. So what rack and TLP mean is that since rack still depends on some ACK, and in the absence of ACK, then you send some probe packets, right? A very small amount of probe packet to trigger ACKs. So rack can continue to do this ACK-driven repairs. And you can avoid like very lengthy timeout because you send the probe packet much faster than the timeouts. And unlike timeout, which you completely reset congestion window to 1 and slow start, in this case, the ACKs sort of events are still coming back within sort of a couple of RTTs, and you can continue to do fast recovery. And that's why we put TLP in here. So how come TLP was expired, our draft, and never make into the TCPM before? Because the main concern at that time is TLP depends on some mechanism like rack. But before it was actually depending on another draft called FAC. So it's a draft depending on another draft. And the FAC draft is actually much more complicated. So at that time, the working group decided let's not merge this because it has too much dependencies. But now with rack, TLP can be there.
Stuart Cheshire from Apple. I have a couple of quick questions. You said that Google sees a lot of tail loss.
Yes.
And I wanted to make sure I was understanding that right. So as a percentage of all connections, it's a small percentage, right? It's 2 or 3%. Is that true?
So if you ask how many connections experience tail losses, that number is not very high. So because I don't know exactly how much of them experience tail losses, but I know how much of them experience some kind of losses, right? At least as one packet loss. That's about 10%, you know.
Okay.
And so I know tail loss is just, let's say even if it's 100%, it's only up to 10%, but it's certainly not that number. Maybe up to 5 or 6%.
Okay,
Yeah.
I think I understand. So the majority of connections don't have a loss, but the ones that do, it tends to be tail loss because they're short.
Yes, timeout repair is the main mechanism.
Right. Yeah. And then the second question, you talk about retransmitting in 2 round trip times. That doesn't sound that different because TCP's normal retransmission timer is the mean round trip plus 4 times the variance. So
that's right.
2 times the round trip could even be higher than the normal retransmit timer.
Yeah, so I think for, so the trick here is that at least for like, say RFC, it actually said that even though it's RTT, smooth RTT plus the variation, it actually has a lower bound of 1 second. And in Linux, the lower bound is actually 200 millisecond. But so if you think of an RTT of say,
I think macOS uses 200 milliseconds as well. I think we load.
Yeah. So you're talking about, let's say RTT is only 10 milliseconds. You're talking about 20 milliseconds versus.
Okay. So now I understand. Yeah. So you're talking about 2 times the real round trip.
The real round
without
trip.
The minimum.
No bound. Yeah. No cap.
Jana Yengar, in response to what you just asked, what is the first question you asked about the percentage of tail losses? It's important to also consider that the cost of every tail loss is substantially higher than the cost of a loss elsewhere. So it's not just the percentage of losses that are tail losses. The cost in time, yes.
Marcelo Oñulo, sorry, I just don't follow the logic. You argue that the problem why the retransmission timeout is too high is because there is a minimum value.
That's right.
And instead of just simply removing the minimum value, you just build all this whole mechanism.
Yeah. So yeah, that sounds a very much straightforward fix, and I agree. Now the trick here is that timeout in TCP actually means that the entire flight has been lost, and essentially all the you have not basically the ACK clocking has stopped. And in that sense, you actually reduce C-win all the way to 1. But if during this time you send one more packet and the packet returns within 1 round trip, you really don't have to have this kind of reaction to say, oh, my C1 was 100. So I think a subsequent feedback was, well, in this case, why don't we just not change the C1? If I reduce the timer and then, repro very quickly and then the ad comes back. Yeah.
So I agree that if you actually receive the SAC of P2 when you retransmit, you don't need to shrink the congestion window. That makes perfect sense to me. All I'm saying is that you probably, at least you want to do both. At least you also want to remove the minimum. If you think that that's a problem, it's a problem in general, right?
So let me rephrase this way. If you consider TOP just as a fast timeout, and yes, you are right. TOP is literally just a fast timeout, and instead of retransmitting the first packet, it chooses to retransmit the different packets. And if you say let's just lower the RTO everywhere, and I think that has a lot of other concerns because of, say, spurious timeouts, right? That has much higher collateral damage. Because now you might be, this C1 might be 200 or 100. And just because one packet didn't come back and RTO has fired, then you say, well, I think we should reduce, essentially start from scratch. I think that's the main sort of problem that RAC and TOP trying to address.
Ian Sweat, Google. I also wanted to add that there are other cases that are more complex than this example, where you save a lot more time than just like, half an hour TT or a few hundred milliseconds, because this allows RAC to use TLP to recover like more than one packet that might be outstanding and other scenarios like that. So I think this is a nice example as an introduction, but like there are a lot of cases when you might like lose multiple.
Yeah, so I actually have a more complicated example in the subsequent slides, which I can show you. Yeah.
Chana Iyengar, just one other thing I want to note is that this is actually, per my understanding, TLP is actually a probe packet. So that's when you do a retransmission, TCP is basically declaring the packet as lost. In this case, that's not the case. Yeah, so it's additional load on the network, but it seems reasonable at this point.
Right. Next slide. So I think we pretty much have discussed what this slide's trying to present. Like, why are we proposing all this? Another heuristic. What we really intend to do is address first all this poor performance caused by the costly timeouts. The other is the complex heuristics that's implemented into the stack. As I listed here, look like how many RFC and drafts that Linux has implemented. And it's really difficult to maintain. And a lot of them is addressed things case by case. For example, if I only send 2 packets, so 3 due back doesn't make sense. So let me reduce to 1 in that case. I can name a few more other examples offline. But again, the idea is to make it simpler and make it faster. The next slide, please. So here is a quick experiment we did to compare essentially the IETF conformance stack and the RAC and TLP. In this case, we both use FRTO because FRTO is part of the timeout mechanism that TOP and RAC does not address. TOP is just a fast recovery. What we've seen here is that TOP plus RAC has effectively reduced the number of timeouts on this Google servers by 40%. And notice that the place I'm experimenting is actually Western Europe. These are the fairly good connections. It's not even poor connectivity, and we can already reduce a lot of timeout repairs. And reducing timeout repair is just speeds up all these recoveries because the total recovery time is sped up by the 23%, with sort of 2%, 3% more data packets, comparing the total number of data packets sent by these servers. So we can, what we're trying to argue here is that there is a bit of increase in the amount of traffic, but with a big returns in recovery speed. Next slide, please. And it's not just web transactions. Here I can show you that on high-speed connections, actually avoiding timeout could be critical. And this is just an emulated connection, 20 millisecond RTT, 10 gigabit link. With 1% random drop, not queue drop. The queue is substantially, buffer is substantially big. And we use a BBR congestion control. It's a new congestion control, which we're going to talk about in ICCRG. But here, the congestion control is not the key. The key here is to compare the time sequence graph of using rack or without using rack. And if you see that with rack, let me explain the time sequence a little bit. The white line is the data line, and the slope is about 10 gigabits per second. And the green line is the ACK line. And the yellow line is sort of the maximum sequence you are allowed to send constrained by the receive window. And since we have 1% random drop, that means about 10,000 packets, there is going to be a retransmission that gets lost again. Because you constantly have retransmissions, and eventually you have a retransmit that gets dropped, so you have to repair. And without rack, you simply cannot detect this kind of lost retransmission, because so far all these due-back approaches only apply to the original packet sent. If a retransmit is lost, then the only way to recover it, according to the IETF spec, is timeout. And
right.
here,
clarification question. So this, when you get this data, it's just a bulk data transfer. It's not the HTTP or something. It's just
it's a net perf.
Okay.
Bulk data, the down, packets. Yeah, nothing. It's not a production snapshot of traffic.
Okay.
But in this case, even Linux is using 200 millisecond timeout. That just means that once you hit this loss retransmit, basically it's complete silence for 200 milliseconds. And with high-speed flows, you get this horrible throughput, which you think, oh, it's all congestion control's problem. But really, you are just not repairing a packet that has been lost again. Next slide, please. So let me go through sort of a somewhat more complicated example of what rack and TLP can achieve. So this is sort of the timeline graph, like a rotated timeline graph, that like what I show in the first slide. Suppose you send 4 data packets in different colors, right? And then they are all dropped, tail drop. And what you do is after 2 RTT, you send a tail loss probe. In this case, you retransmit the last green one, and you get an ACK. And with that ACK comes back, then you look at, well, what about whatever that hasn't been ACKed? That would be the blue packets, the red packet, and the yellow packet. They have all been sent for 3 RTT ago. They must have been lost. So you go ahead and retransmit them. But unfortunately, they also get lost altogether again. And in this case, you sort of did the same, but in this time you retry with the yellow packet after 2 RTT. And as you continue to generate this ACK stream, essentially rack will pick up, like detect whatever packet is lost. Doesn't matter how many times this packet has been retransmitted, because rack only look at the time. He doesn't care about the sequence numbers. And in this case, you can repair all the packets in the unit of RTTs instead of timeout. And next slide, please. So this slide just shows you the bottom is the same graph. The top is when you don't have rack and TLP. When you have a tail drop, then the only thing to do is to have a timeout. And in order to show how it can repair with timeout, I actually make the timeout just 3 RTT. In reality, it could be larger, and often larger, a lot bigger than that. So you like on the top graph, you have a tail drop, then you got then essentially you timeout, retransmit the green packet, and then you do this slow start. So you get an ACK back, you send the 2, and then you get them lost. And then you just have to timeout and timeout and timeout again. In the end, depends on how many packets are actually lost. It will take you a lot longer to repair. And that's the key difference is rack and TLP just trying to maximize ACK-driven repairs as much as possible. And next slide, please. So just a couple interesting discussion would be, why do we want to retransmit the last packet instead of the first packet? Because the reason we did this is because of previously TLP needs you to depend on FAC. And if you just simply retransmit the first packet, FAC won't be able to tell that, oh, actually anything sent past the first packet has been lost. But actually, we're looking to revise that. We might be able to just retransmit the first packet. It actually has one benefit because of TCP is in order delivery, meaning that on the receiver, if you just has repair the last packet, essentially the receiver still can receive the whatever data, the last packet in it that's in the last packet. So in this case, retransmitting the first packet is actually more beneficial because the receiver can start working on whatever packet gets retransmitted. And there is also some corner cases when, what if they say you only have one packet lost? You only send one packet and you didn't hear back, you retransmit the TOP and you accidentally sort of repair it. And in this case, you might actually say, oh, I repaired it, so let's move on. But in reality, there is actually a packet loss event, right? It's a single packet loss. And are you supposed to let congestion control know about this? You send one packet, get lost, and I repair it. So you might as well, if you are loss-based congestion control, you should do something about it. And we did have a mechanism to detect that, but it's somewhat complicated. Using sort of the heuristic like dewbacks and the DSACs. And the question would be, if you just send one packet and you get, and that packet gets lost, do you really absolutely have to feed this back to the congestion control to do something, or are you like, all right, no big deal, let's move on? And in that case, you could have double the amount of traffic on this connection, but it's a thin straw. So I think it's worth a discussion in the list. And there are also, well, how many TOP do you send? Because TOP can get lost, right? You send a probe and it also get lost. Do you retry again and again and again? So basically, like, you never really go into RTO. This could also be a problem. So in our current trial, we just say we retry once, and if then that doesn't work, fall back to RTO, because it's long enough that nothing has ever come back. So you really should take actions on it. Last question would be, sounds like we have a lot of timers. We're talking about TOP timer, rack reordering timer, and also the canonical TCP retransmit timer. Sounds a lot of overhead, but in reality, in our implementation, we only use one timer. Essentially, this timer is like, when do I retransmit something, next? So at any time, you only have one timer available. You don't need to have put actually 3 timers. Please.
Hi, my name is Martin Duke. This is an interesting idea, but of course RTO drives us to slow start, because when you lose a lot of packets, as I think everyone knows, that signals a lot of congestion in the network. So this method and in your example, you had 4 packets wiped out at a time. Are you essentially seeking to abolish slow start for loss recovery? And if so, wouldn't a more straightforward method to be just to revise the slow start response is not appropriate in the internet anymore?
I think it's so we have to go look at. I think the original definition of timeout and slow start was that the entire flight has been completely lost, and you wait for a very long interval and nothing has come back, right? So it sounds like it's a severe congestion, and that's why you want to sort of reprobe the bandwidth. That's why this sort of on timeout slow start after RTO. But in this case, what we're arguing is that if within, say, 3 round trips, we send some additional data and actually gets the ACK come back, then we argue that you don't really have to restart from scratch. So in some sense, we are modifying the congestion control behavior in that sense by claiming that, oh, if there is indeed a timeout, it's a TOP timeout, but we feel like it's only within 3 RTTs. You don't really need to have such a dramatic congestion control sort of reaction is what we are really modifying. So in some sense, we are modifying the congestion control behavior on the connection, just not the congestion control algorithm itself.
Jana Iyengar, I do want to draw a distinction here. Again, the difference is that in TLP, the packet is actually not marked as lost, which means that the sender has not said that the packet is actually dropped in the network due to congestion or whatever. And it's closer to sending after a pause than it is sending after a loss. So I think that distinction definitely holds. And sending after a pause, we usually send the entire congestion window, not a reduced congestion window.
That's right, yeah.
I mean, I agree to Jana. I just have still a question because you said you want to avoid to go down to the minimum congestion window. Did you just try to halve the congestion window, and if you know what the impact would be? Because I guess you are in a situation where you anyway don't have a lot of data to send, so probably you don't need a very large congestion window.
Yes, in reality, we are actually doing that because what happens is, let's say we send the TOP probe and the ACK comes back, and we detect some packet that are lost and needs to be retransmitted. We actually go into fast recovery. So if we are using Reno, then yes, we are having the congestion window in that sense. Yeah. Next slide, please. So let me just show. We talk about the slow start after timeout, and I can show you an extreme interesting old problem in sort of timeout, slow start after timeout. So let me just use this imaginary sort of time sequence. Jana, do you have?
Jana, I have a question about what you just said. I'm happy to wait until later if you think that's better.
How about we wait? Because I'm a little bit running out of time. Let's say we have a spurious timeout, right? So what Linux does today, and I think that's also conformed to this IRC, is we say, all right, whatever that's remaining have been lost. And then we reduce CWIN to 1 and we transmit the first packet, right? Then actually it's the spurious timeout. So the ACK of the first packet comes back. Then we say, oh, look, my retransmission is effective. Let me retransmit the second and the third one. And then the ACK comes back, then you essentially end up retransmitting the entire flight. Next slide, please. And this has shown up in real production. So this is trace taken on Chrome, downloading a lot of images from pin interest. And this is showing the number of packets per second that the Chrome browser is receiving. And the gray area are the original packets. And the blue area is sort of spuriously retransmitted packet because of this case. So what happened is the Chrome essentially opens a lot of connections to different pin interest image domain names, right? And then there is this sort of an incast problem where lots of packets are coming back, and the delay suddenly shoots to some much higher number, and the RTO wasn't able to cope with that because the ACKs and the data in this case are on Wi-Fi and they are fighting with the channel, so the ACK can't even come back in time. But essentially the queue has grown up way up, and eventually we have a timeout, and not just one connection having a timeout, a ton of connections are having all this spurious timeout, and they are suffering this sort of spurious retransmission storm. So we end up essentially retransmit every image twice in this case. And let me show you how RAC and TOP, next slide please, could have avoided this problem. Essentially what happened would be that on the spurious timeout, instead of just claiming every packet is lost, right? You use sort of the concept to say, let's send some scout packet to see what's going on. And in this case, we send the last two packets. Let's say there are 100 packets, we send P99 and the P100 instead of the first packet. And if the next ACK that we get is for some packet that we have never retransmitted, which in this case would be an ACK of P1 or an ACK of P2, then we say, look, I never retransmitted this packet and now I'm getting an ACK. So this must be a spurious timeout. So literally you still retransmit some, but it's very, very little. It's like 1 or 2 packets in this case. And you can cut this spurious storm much early on. And essentially that shows how sending this scout packet to sort of confirm what's going on could be very useful. And you can use RAC and TOP to replace the existing sort of on timeout, let me just mark everything lost and retransmit everything issue. Next slide, please. So to conclude, I think this is the sort of the new way we like to do loss recovery based on time. And it's conceptually more intuitive. Just consider so you get ACKs, right? You're looking at when did I send this packet, and is this time make sense? And if I have some reordering concerns, let's wait a little bit more. And you can get rid of all this sort of due back threshold drawbacks. That's 3 due backs, or if you send a lot and get the last packet delivered first, the due back threshold in Linux right now is adjusted to the CWIN number. And next time you send 2 packets, then that's all screwed up. So it's also robust to the reordering. And as we are continuing to experiment, we would like to progressively retire this dewback threshold on at least our servers, like replacing it as rack. Rack right now is sort of a supplemental recovery. Like if dewback approach didn't conclude some packet have lost, we use rack to detect more. And this algorithm has already been sort of implemented in a few platforms, Linux, Windows, and FreeBSD stack that Randy is working on. So here I would like to ask more reviews, and especially implementation feedback will be great because TLP ultimately requires per packet timestamp, at least at millisecond granularity. And it may work on Linux, but we don't know if it works well on other stacks. It might have other difficulties. Thank you.
Stuart Cheshire again. A quick suggestion or request to you. You compute timeouts as 2 times the round trip or other multiples.
Mm-hmm.
I think it would be good to take the variance or the jitter into account, because one of the criticisms I hear leveled against TCP is it doesn't cope with wireless networks, be that LTE or Wi-Fi, because of the variability. When you get interference, the Wi-Fi access point responds by lowering the data rate, retransmitting multiple times, and the packet still gets through, but that results in big variations in delay. And if you have a fixed multiple of the round trip, you're not taking that jitter into account.
Yes, I agree. Right now, this tool sort of SRTT is really just the first step, and we plan to experiment. Like some people have argued that not just the RTT variance, but let's use how about the most recent RTT that might be even more up to date than the smooth RTT. So we plan to experiment all that. Thanks.
Hello, this is Yoshi from Floor. So first question is, in this draft, you don't define congestion control, basically. And then how, why we can have an implementation without having congestion control logic? Why we can have a Linux implementation, Windows implementation, FreeBSD implementation, and so on?
So you mean, so first we did talk about, in the draft, we talk about interaction with congestion control. And I think the interaction is that rack is just a loss sort of detection algorithm, rack plus TLP, right? It declares a packet is lost, and when he declares there is a loss event, he informs congestion control about it, and it's congestion control's job to decide what to do. So rack does not has any sort of mandate on CWIN changes or anything.
So each implementation has its congestion control logic for rack. Is that what you're saying?
Yeah, so for example, I don't know what congestion, I think for Windows 10, maybe it's using compound. And essentially, it probably has some logic saying, if I'm entering fast recovery, what do I do? So in this case, when rack detects a new loss, it's just going to switch to the fast recovery sort of handler in Windows. But I can't really speak for it because I never look at the code. Yeah,
because I see fundamental difference between this and the RFC 5681 is, in case of 5681, if the first goes to the fast transmission phase, and then if it fails, if it cannot recover the fall, it basically goes to timeout. But in case of rack, it's keep continuing the retransmission, in my understanding. And then when you do retransmission, what do you set the pipe size? It's back off or it's out of?
So actually in RFC 5681, the congestion control RFC already has a line says that if retransmit has been lost again, meaning that there is a new loss event in another round trip, then congestion control should consider that as another loss episode and then reduce the window again.
Usually second time, most likely fast recovery will fail and then goes to timeout.
Rack is exactly trying to change that.
Right.
Yeah.
the behavior is very different. That's what I
Okay, so the action item I take is that there needs to be more clarification about this detailed interactions of fast recovery, rack, and the congestion control in the draft.
Okay.
Thanks.
Hi, Bob Briscoe. Just a sort of procedural thing, really. Is the TLP stuff, are you intending to sort of make that a requirement for when you implement rack, or just to optional thing, an optional thing that you can add?
Yes. So in the draft, we did say this is sort of a supplemental optimization to rack, but it's a major optimization because without it, you don't see much speed up on the recovery. Because if you have tail losses, there is no way rack can do it. It relies on some ACK. Yeah.
Yeah, I was just thinking, like in say in a data center where you're using ECN, maybe you don't worry so much about TLP, so you don't have to be required to implement it.
I see. Yeah. So in the draft, we did say that it's not required, but it's like a recommended implementation.
Can I comment on that? I started actually implementing just rack without TLP, and I found it had a lot of lacking things, and it finally dawned on me I had to implement TLP to actually get the performance I needed. So we actually implemented them together because they were really just kind of essential to make it work really well. So, pardon? Of course.
If you don't have losses, you don't need rack.
Rack doesn't even come into play if there's no loss.
Are we actually going to talk?
Can you clarify what's the difference? Transmission losses and Oh, okay. I see.
Oh, we're not talking ATM now, are we?
Yeah.
So one suggestion here would be that if it's rack plus TLP, I would perhaps even call the draft something slightly different. I haven't seen the latest version of the draft, so I don't know what it's called. I like having TLP in here. To Yoshi's point, I think you're exactly right that I think that this actually updates 5681 in some odd way. But I think I also think it's completely appropriate. 5681 has for long confused.
confused.
Well, confused. Yes, conflated. Let's say conflated. Has mixed loss detection logic with congestion control actions, and exactly what should be retransmitted as well. Being able to separate that sum is not a bad thing.
Okay, that's good.
Thank you.
Thank you so much. So next, Marcel.
Okay, Marcelo Bagnulio. I'm going to present this draft about adding ECN support to TCP control packets and retransmission. I already presented a first version of this draft in the last meeting. This is a 0.0 version because this was the other draft was submitted to TSVWG, and now we're submitting this to TCPM once that we understood what's the right home for this. So the difference between this draft and what I presented in Berlin is that in Berlin, basically we presented the arguments for doing this, and now assuming that people are okay with doing this, I'm presenting this new draft contains how you would do that. Okay, next slide. So the goal is to add support to TCP control packets. That basically means SYNs, window probe, Purax, fins, resets, and also to retransmissions, right? So as current ECN specification precludes from marking with ECN this type of packets. So the goals of this is supposed to be an experimental RFC. It actually falls in under the umbrella of David's black draft that is going to present in the TSVWG tomorrow. So this is one of the experiments that falls within that, and the goals of the experiment will be to see how the network reacts when you start doing that, including both the routers along the path and the existing endpoints, right? How much performance you actually gain if you do this, right? And identify any potential issues with this. Yes.
Yuchang Chen, how come retransmission doesn't have ECN support in the current draft?
That's what the ECN RFC says.
Did he explain why not? I was very surprised to learn that.
They actually explain why not, but I don't remember right now.
Okay.
Actually, it's in my draft, but I just don't remember it. Sorry, I have.
Okay, because to me, retransmission is just a data packet. Why make it spatial? It's quite surprising to me.
I cannot answer that. I have like an 8-hour jet lag. I arrived yesterday, so I'm a bit brain dead. So I'm sorry for.
Okay, David is coming.
Ilpo Järvinen, is it because ambiguity problem, so you don't know which of the packets original the retransmission was affected in case of TCP?
David has comment. Right.
David Black.
Somebody said it doesn't matter, but it matters if you have multiple of them in a window, or actually in two windows then.
David Black, one of the original authors of 3168, although I'll admit I wasn't the expert on this stuff. Staring at the back of Stuart's head, this was before Apple rolled out ECN and helped wipe out ECN black holes. Back when 3168 was written, there were some widely deployed equipment, and I won't name names to protect the guilty, that discarded anything that had the ECN turned on. Hence, I believe that was written the way it was, so that if you hit one of these pieces of bad middle box behavior, the retransmission would get through.
Just clarification question, Jana Iyengar. Does this mean that, that seems like an odd optimization, doesn't it? Because then you send a transmission, doesn't get through, send retransmissions, and then now again you send things with ECN, and then you again drop them, and then you go back.
Reliable detection of middle box behavior is still a research topic.
Bob Briscoe, I've just checked your draft that quotes 3168, which David wrote, and it says it was to prevent DOS attacks, and the logic behind that is what you questioned we questioned in the draft, on the basis that the idea of this DOS attack was that a packet could be sent, or a retransmission could be sent with ECN on, and then the receiver would have to accept it. And actually, to be honest, I couldn't quite follow the logic in 3168 either, but it's to do with DOS attacks. Yeah.
Right.
Yep.
I'm happy to actually forward to the mailing list the argument in the RFC. Sorry if I couldn't actually answer this question. So, okay, next. So I divided the draft in two parts, in the router behavior or the network node behavior and the endpoint behavior. Right, from the router behavior, basically, what we're saying is that if you receive any of these packets with the ECT or the CE code points on, you should actually treat them as you would with any other packet that is legitimate, right? So if you're congested, you should mark it with C. If you are not congested, you should simply forward it, not discard it, because it's a legitimate packet, right? So next slide. So for the endpoint behavior, we describe different for different cases. So for the SYN, there was this question about what type of endpoints are going to support this updated behavior, right? So currently, Accurate ECN has most of the logic in order to support that. There are some pieces missing, and what we describe in the draft is how to update an accurate ECN endpoint to support marking in the scene. What we're not covering in the draft is if you have an ECN endpoint that is not accurate ECN, how this would support marking in the scene, right? This is a case that we are not supporting, right? So basically what we're doing is we're leveraging on the logic that it's already in the accurate ECN draft in order to update its behavior, right? So the format described in the draft is fully compatible with accurate ECN, and what we do is just we include the missing pieces in that draft. Next slide. So what we do is basically say that the sender should send, the client should send the scene mark with ECT0 or ECT1, right? And depending on the different situations about what he receives, how he should react, right? So if he receives a CNAC with this flag combination, that basically means that accurate ECN is supported and there was no CE in the scene, then basically the client continues with its initial congestion window and using accurate ECN. If the CNAC is received with this combination of flags, that basically means that accurate ECN is supported and there was a CE in the scene, so the client continues with with accurate ECN, but reduces congestion window to 1. And if the CNAC is received with this combination, that basically means is that neither accurate ECN nor this particular spec, this experiment supported, but RFC 3168 is supported. So in this case, the client should continue using RFC 3168, but we don't really know what to do with the congestion window because there could be a mark in the scene that we're not knowing about because the endpoint, the server does not support marking in the scene. So in this case, we need to figure out what congestion window to use. We don't have any information to do that. We can keep the initial window, we can go back to 1, or we can do something in between, right? The problem with, the problems are obvious here, I guess. If you keep the initial window as it is, if you had a mark, you're just disregarding this congestion signal. If you go to 1, then people adopting this experiment will be penalized always, right? And if you do something in between, then you're always a bit penalized and you're always forgetting a bit of congestion. So any opinions here would be useful. And same situation with the CNAC with any other combination. That basically means that RFC 3168 is not supported. And in this case, the client continues with ECN, and we also don't know what congestion window to use in this case. So if anyone has input on this, it would be useful here on the mailing list. Next slide. So again, here in the PureAC, we're saying that PureACs can be marked, and if the endpoint receives a congestion signal, it will basically react as any other packet. It will reduce the congestion window. The problem is, the potential problem, it's not really a problem, but is that what happens if the endpoint is only sending PureACs, right? So reducing the congestion window doesn't have any immediate congestion relief effect. So you could explore some other means to reduce the load, like increasing the number of ACs until you send a duplicate ACK or something like that to reduce the number of ACs. I think the effect of this will be so negligible that probably it's not worth the effort, but just for completeness, I'm just sending this. Okay, next slide. So in window probes, again, we're just saying that you should mark window probes with this, and you have a similar situation here in the sense that if by the time you receive the congestion notification, you have increased the receiver window, then you're okay, right? You simply reduce the congestion window and you are appropriately responding to congestion. However, if you still have a receiver window of 0, then there is not much. There is not much of a congestion response that you're doing because you're only sending the window probes periodically, right? So you could reduce the load by increasing the time that you use in order to send the window probes. But again, since the time is already very, very long, right, it wouldn't actually reduce much the load. In any case, you are still reducing the congestion window. So whenever you have the receiver windows open, you will be reacting to congestion accordingly, right? So probably that's good enough. Next slide. So with fins and retransmission, we're just saying that can be marked. There is not much to do about this. And with resets, it's hardly useful as a congestion notification mean, in the sense that if a sender is sending a reset, basically means it doesn't have a congestion. So there is nothing he will actually do in order to reduce the load of the network. Basically, the goal of actually marking this is to avoid to being preferentially discarded in case of congestion events, the reset. Yes, Bob.
I don't know whether you want to know. I've just sort of worked out what the retransmissions thing is. Are people interested? Yeah. The 3168 said that when a receiver receives a out of window retransmission, or there could be a DOS attack where someone's spoofing the source address and sends something out of window to the receiver. And so 3168 says the receiver should ignore any CE marking on an out of window packet. Oh, and then it also says that senders shouldn't send it as well, right, which is sort of unnecessary because the receiver's ignoring it. And that's why we're now saying, well, why don't you let the sender set it? Effectively, what the RFC is trying to do is say DOS attacks shouldn't set this, which is a bit silly. And it's perfectly okay for normal users to set it. Pardon? Sorry, once again? No, a DOS attack could, because it doesn't know the
it's easier. It opens the vulnerability window because you just send any packet with any sequence number. It's considered to be a duplicated packet. Then it will actually force to reduce the window, right?
And the other argument in 3168 regarding retransmissions is that if they're dropped, the receiver won't know about them. But if they've got a CE marking on them, the receiver will respond to it. Therefore, don't allow ECT on it. So you can't have a CE marking because you will be ignoring the CE marking at the other end. But we figured when we wrote this draft, well, if it's equivalent to the drop case when you don't even get the thing, therefore, and you don't know that you haven't got the retransmission, then you haven't lost any more congestion information.
Okay, that's okay. So next slide. So we believe that the draft is pretty straightforward. There is not, I mean, except for the question about what to do with the initial window in the cases where the endpoint does, I mean, the server doesn't support this. I think that the remaining parts of the draft are pretty reasonable. There is no much controversy around this. So we are doing a number of experiments to see whether these can work. I mean, whether these type of packets are dropped by the network or by the servers. There is existing previous work on this area. Media and Brian has had a paper on PAM published trying to measure some of these things. So we are doing another measurement campaign along the same lines and adding all the rest of flag combinations that this draft address. Hopefully we will be able to show the results by the next meeting. And with this, again, what I would ask is for people to read the document and see if they're happy with it.
A couple of questions. Yes. So as far as I read this draft, the intended status was information, but let's talk about this pretty experimental.
No, I'm sorry. That's my mistake. It should be experimental. Sorry, that's just.
So please update
Yes.
the next version.
Yes.
And so then I think this is very similar situation like alternative back-off draft, in my understanding. So once David's draft has been accepted, we can think about the call for adoption. Does that make sense?
That's perfect. Again, as I would ask people to read it and comment, see if you think this is reasonable.
Right.
Okay. Thanks.
Thank you. Okay, next one. Yep, Jennifer.
Yeah, let's begin. Hello, this is Jennifer. Today I will introduce an improvement of ECN, which in some way can enhance TCP fairness problem. This draft was originally written by my friend Marcus, but unfortunately he cannot show up today. But he is right now online with us, so if you have any questions, just feel free to ask him. Next page. As we know, in RFC 3168, the ECN protocol, it allows end-to-end notification of network congestions. The congestion experience sign can be marked by any of the device inside the path, and the TCP receiver will echo this congestion experience sign to the TCP sender through acknowledgement. Then the TCP sender will adjust the send window size according to the congestion window size and also the ECN labeled packets ratio. But we think there is a little minor defects inside current ECN. First of all, it cannot precisely reflect network congestion status. Imagine when multiple network devices exceed their threshold value, then each of them can change the ECN field inside the message it transmitted. Therefore, the total proportion of ECN labeled packets going to be transmitted in one RTT might be larger than the proportion marked by the worst congested node inside the path. That means the TCP sender received congestion status might be greater than the actual link congestion level, which we think is better described by the worst node status. Next page, please. There are also some other limitations. In current ECN, it lacks of a good solution for light-load network situation, since it only deals with congestion. If network is light-loaded, there is no rapid notification scheme to TCP sender, so the TCP sender is unable to rapidly adjust its send window size for a better utilization of idling physical bandwidth. Yes, please.
On that point, if the network is slightly loaded, why would you get ECN marks anyway?
It's not some disadvantage of current ECN. It's just something we want to add to the current ECN. Because the current ECN is only dealing with the congestion status, kind of congestion control and avoidance.
Okay, well, I'll hold my question.
Sorry. And next page, please. And we think there is also a TCP fairness problem. In current ECN, when several flows are going to be transmitted in the same path, then they are possibly to attain different link congestion status. That is because the packet transmission order inside different flows is depending on the flow's own sending rate. For different flows, the amount of packets being sent out in one RTT may vary. So if congestion ever occurs, the proportion of ECN labeled packets in different flows may also vary. This is a kind of unfairness between flows send window adjustment ratio. I think this unfairness problem is obvious when several flows are in same business scenarios and protocols. Assuming that the three receivers are requesting the same sports game live show streams, which are all in 4K resolutions. If the three flow attain different link congestion level, they will adjust their flow rate, transmission rate differently. Therefore, even if they are in the same contents and protocols, the flow rate will vary. Next page. What we are going to do is just to solve those problems I have just mentioned. We will do an improvement of ECN scheme in which it can not only reflect the worst congested node status for more precise congestion control, but also fully utilize the link idle rate in network lie low situations. And the last but not the least, we also want to achieve more fairness between different flows.
Last second. So you're bundling together quite a few different things here.
Mm-hmm.
Several of which I think are actually limitations of TCP that ECN was never meant to actually fix. So it's a little bit misleading to say ECN has these limitations, right?
Yeah.
It would be probably better to say that your ECN scheme can also improve these things that are TCP limitations.
Yes, that's really what we want to say.
The middle point here I still don't understand, right? So a lightly noded network is one where the offered load doesn't exceed the capacity, right?
Yeah. That's it.
In such a case, you will not be able to utilize the network because you don't have enough traffic.
Yeah, so in that case, the network is okay to be light loaded, but if there is more traffic waiting to be transmitted, but the sender doesn't know there is idling bandwidth, we are kind of solving for this kind of problem.
But the sender will, if the sender has data to send, it will try to increase its rate.
Yes, but it's slowly. What we
Okay.
mean is there is no rapidly notification scheme to the TCP sender. Yeah.
Jana Ingar, perhaps I don't understand the first point. To be honest, I'm not sure what it means. What is the worst congested node?
That means maybe, for example, there are two nodes inside the network path. I mean, two routers or two network devices anyway. So maybe there are 10 packets to be transmitted in one RTT, and then maybe the one of the packets was marked CE by the first node inside the network path, and maybe the other two packets are marked CE by the second node. Then for ECN scheme, the total ECN labeled packets is 3, right?
Oh, I see.
Yeah. So
It seems you're assuming proportional marking,
yeah.
which ECN is actually not doing, right? So there's accurate ECN proposals that we have are going that direction, but pure ECN doesn't have any proportionality to the markings. Okay. So I'm just trying to get to.
So yes, you need accurate ECN to get this information at the sender to feedback. But I mean, the information you have at the receiver is the number of marked packets, right?
Right.
So like whatever is an IP on ECN supports this, but you're right. You need accurate ECN.
Yeah, I mean, there's nothing in the ECN design lets you identify the worst loaded anything without accurate ECN or even with accurate ECN, right?
So I want to actually make another point which doesn't make this discussion, or which we don't even need to have this discussion because it's actually not true. So if you have two points that are marking ECN, then the total congestion, like the 3 marks you get, is the actual congestion in the link. Because, for example, if you have congestion here and then later on the pass over here, and you would increase the capacity over here, and there's no congestion anymore, that means there's just more congestion over here. So even if the congestion marks sum up over a whole pass, that's the pass congestion you have. So that's correct.
Okay.
That problem just doesn't exist. That's the pass congestion. That's what you should work on. But you don't even want to know that. I mean, what's the worst node? Yeah. So what you really want is the pass congestion. That's what you get.
Jana Ingar, I'm still confused. about what the worst congested node status is. I mean, it sounds like from the discussion that just happened here that maybe with accurate ECN, what you described as marking would give you total path congestion. But that's still not worst congested node. I mean, so if I think of the router that has the most congestion as the bottleneck router, then that's the one that should matter. If your flow is going through that node, then the marking at that router should matter.
I think by using the worst congestion node status here is just simply means the one node inside the path which marks the most amount of CE sign. Yeah. So.
Can I try and explain, Bob Briscoe?
Yeah.
Because I reviewed this for them, and also agreed with previous speakers that this is a feature of ECN, not a bug. That ECN gives the approximately the sum of all the congestion on the path, not the worst. And what Jing is trying to do is just give the worst congestion, which in the mechanism they'll show later. And I figure that you actually want to know if there's more than one congestion on the path. You want to know that you've got more congestion on that path for one flow, whereas maybe another flow that's just going through one of the points gets less congestion, and that's actually a feature of ECN. Whereas what they're trying to do here is find the worst case, which actually gives you a lower level of congestion when you've got more than one point, and I think that's incorrect. But the other side of this scheme is maybe more interesting. Yeah, or at least it's trying to address a problem that I think is more valid, whereas I'm not convinced this is a valid problem.
Thank you.
Just to add one more point. So if you actually have two queues on a path, then you don't want to just reduce one of the queues. You want to reduce your sending rate so you can remove both of the queues. So you need the total congestion.
So if you have more questions, let's just discuss afterwards. So I have enough time to explain. Thank you. The next page, please. Here is a detailed improvement. The TCP receiver will notice the TCP sender with the worst case of network devices. Let's see how it works. The TCP sender will send out the message. The network device 1 receives the message and looks up its forwarding table to find out the right output port. Here is port 1. Actually, the network devices are obtaining the congestion degree or the idle rate of every output port periodically. So the the device 1 will add its current congestion degree or idle rate of port 1 to the IP header of the message, then send out the message. The network device 2 will only update the IP header if its current congestion degree or idle rate of port 1 is worse than that in the message. Otherwise, it will do nothing more than just simply transmission. Then we can see that the message is sent out with the worst congestion degree or link idle rate inside its IP header. The following network device will repeat the same steps until the message reaches to the receiver. The TCP receiver will then echo the most congestion degree or the link idle rate information in its TCP header inside the acknowledgement to the sender. Then the sender will adjusting its send window size according to the detailed information inside the acknowledgement. Here we define congestion degree and link idle rate. We describe the congestion degree just as the time it takes to complete message transmission inside the link cache. For example, if cache size is 20 megabytes and the link bandwidth is 1 gigabps, then we describe the congestion degree as 0.16 seconds. And also the link idle rate, just simply the opposite to the link usage. I think everyone can understand it. Go ahead.
So cache means queue?
A buffer
contents. Okay.
Yeah.
The other thing is sort of, in order for me to think about this, is this like XCP?
Sorry?
XCP was a Dina Katabi. I don't know if Aaron's in the room, but it sounds seems like it's what you're doing is XCP-like, right?
I'm not sure.
Okay.
Is it?
Janayanga, it sounds similar, but so you're basically putting idle rate information inside the IP header. Where in the IP header are you putting this?
I have a slide later
Okay.
on to describe whether where to put it.
Okay.
Okay.
Yeah, it sounds like XCP, similar to it anyways.
Okay, next, I think. Thank you. So we offer two options for send window adjustment. Option one is the TCP sender will adjust the reduced size of its send window according to the worst congestion degree in the received TCP acknowledgement. And the option two is the sender adjust the increasement of its send window size based on the worst idle rate in the received TCP acknowledgement. Here we list an example for the option two. We are assuming that the worst idle rate in TCP acknowledgement is 40%. Then the current send window size of flow 1 is 1,000, while the current window size of flow 2 is only 200. Then the current link utilization, or we can say the total flow rate, is only 60% of the physical bandwidth. Then the flow rate can be theoretically increased by 40% over 60%. That is equals to 66.67%. So the send window should be increased by these two sizes for each flow. And next page, please. Oh, I'm sorry.
That's like I said, an instant. So you're trying to increase the flow rate in one step.
Yeah, because our solution or our idea is not mature enough. So maybe here it's a first solution we have right now, but I think it's discussable, flexible.
Okay, so
if you have a better idea,
this is the target. So I mean, I'm concerned with how you're going to make this adjustment, right? Because if you're doing it in one step, what about new flows that exist that you didn't know about when you got that information, right? So it seems like you want to gradually ramp up anyway, and then it's not so different from what we currently do.
Yeah, I think that's a good question. So we can discuss it later and have a better solutions, I think. And next page, please. And we do a TCP and IP option extension. In the IP packets, the congestion degree and link idle rate can be carried in the IP option field with a 4 bytes length, and also its value is in flow type. And also for TCP acknowledgement, the worst congestion degree or the worst link idle rate can be carried in TCP option with the 4 bytes length and value in flow type. That's what we are doing, answering your questions, I think. Next page. So in a summary, why we say there is a TCP fairness enhancement, because in the same path, each message is carrying the same worst node status, no matter its congestion degree or the link idle rate. Then TCP sender is no longer adjusting its send window size according to the total ratio of ECN label packets. Instead, it will adjust the send window size according to the precise worst node status, which are carried in the TCP acknowledgement. Since each TCP flow attains the same worst node status, then TCP sender will give them same proportion in send window adjustment, which in some way we believe it can improve their TCP fairness between flows. Next, please. For next step, first of all, I need to thank you for your comments, useful comments so far by Bob, Mia, and others. And I think we request your read and more useful comments later on. And we are here today just to raise the problem, raise the question, and let's discuss whether these problems are worth doing or is valid or not, or something. And I think we will do more experiments and verification later on. And actually, we are already doing some, and we will give some more statistic report supports in the next version. And we may also raise some new methods for more rapid notification to TCP sender or other things. Thank you. Go ahead.
Last second. So I think you should take this to ICCRG.
ICCOG?
ICCRG.
ICCRG.
Because
okay.
so for TCPM, I'm unconvinced of the problem motivation. The solution seems very complex and very fragile. And if you did experiments, I think you would find that it doesn't work. For many of the goals, you have, for example, this fairness thing, right? Only works if everybody has the same RTT, because if we all compute the fair rate, but I have 200 millisecond extra delay, my reaction is always going to be slower, and therefore we're never going to hit the goal you want. So I think you need more time that TCPM can give this.
Right.
Yeah, I think the solution is maybe, as you say, it cannot work right now because it's only a thought we didn't put into.
So we don't standardize thoughts, right? So this is why I think ICCRG is the right place.
I'm sorry, because we are already like doing experiments, so also we can change solutions later on. So what we want to see today is the three problems really exist and really need improvement. Yeah, that's the point. That's the main idea.
Jana Iyengar, as ICCRG chair, I agree with some trepidation, but I agree that work like this should go in ICCRG first. I will also say that this is, as Lars pointed out earlier, this is the solution that you suggested and various things that you had in the going as feedback suggests that there's a very strong connection to XCP, which if you are not familiar with, I would recommend that you look up and read, because that has a lot of considerations about fairness as well. And you may want to look into that to see if there's anything you can glean from that for your solutions.
Okay, thank you for your suggestions.
Mia Kulevin is JavaScript. So there's a comment by Michael Scharf, one of the co-chairs, that there is RFC 6077 published by ICCRG on open research issues in congestion control, which also mentions XTP and other stuff. So you should really look at that because it's some stuff is explained there.
Okay.
Then also I have a comment. I think you're actually talking about different mechanisms here, and none of them are really related to ECN, so you shouldn't call it ECN.
Okay.
One is handling congestion, right? The other one is handling idle rate, which is something completely different. And then also signaling this information and reacting to this information in congestion control are two separate things. So you're basically also proposing a new congestion control scheme here, which is like also complex. You should really separate this out.
Okay.
Just Ilpo Järven, just another comment from this RC 3077. So you use this current link load in some part of the method, and it's also somewhat open research question how to actually measure the current link load. So you should probably also look to that and see if there are some issues in your approach related to that.
Okay, thank you.
Jana Iyengar, last comment. In addition to what Maria said about this not being specific to ECN, I want to say this is not specific to TCP either. Because really what you're talking about is flow rates and ECN signaling, which is not at all specific to just TCP. This squarely belongs in ICCRG.
Okay, thank you. And that's all.
Okay.
Do you have any more questions? No.
Any more questions?
Okay.
No question. Okay, thanks so much. Next. Yeah. Okay. So please go ahead.
Okay. So my name is Neil Cardwell, and with my teammates Yu-Chung Chang and Eric Dumze at Google, we've been working on some stuff, and we'd like to kick off the process of taking some new options through the IETF. So specifically, these are options targeted at lower latency. This includes two different features, basically negotiating a maximum ACK delay and microsecond timestamps. Thank you. So the motivation here, not surprisingly, is performance. So we'd like lower latency, higher throughput. So the motivating impetus here is that data centers, even with commodity 10 gigabit Ethernet, have very low latencies, well below 100 microseconds, and we're well on our way to 10 microseconds. And this means that there are some fixed parameters in the TCP world that are a little bit out of date now. So a couple that we're dealing with here are TCP timestamps, where the granularity allowed by the constants in the algorithm for the RFC means that the finest granularity that you can have for TCP timestamps is 1 millisecond, which is well above the RTT in data centers. Another constant that's a little bit out of date is delayed acknowledgements. Typically, these vary, of course, depending on the OS, but typically they're going to range between 40 milliseconds and 200 milliseconds, which again is well above data center RTTs. And then there's a related parameter that's the minimum RTO of 1 second, which again is now well over, orders of magnitude above the RTTs we have in data centers. Yeah, Bob.
Hi, Bob Briscoe. I don't think the granularity of TCP timestamps is specified. It's just agreed out of band or sort of some sort of God knows about it.
I think I mean I think most people have that impression, but actually if you read the RFC, it actually goes through the reasoning for a particular range that it allows, and it turns out the issue is basically the question of how quickly these things can wrap, and then a particular a course of action you need to take for that. I'll get into the details later on. If you look in the RFC and look for the constant 24 days, you'll find it.
Because the reason I say this is that Mia and myself did some work on this earlier with Richard Scheffenegger, and although it's maybe specified somewhere, you can use the timestamp if both ends sort of agree. You can use it as a sort of opaque blob and put your own resolution in there. You don't have to.
Right. The issue is both ends have to agree what it means in terms of pause, because for pause, if it's idle for a long time, then. So basically, I agree. If both sides agree, you can do cool things. And this is basically about a mechanism so that both sides can agree. Yeah.
All right. Hi, Brian Trammell. I'm a co-author on the follow-up draft of that draft, which was an attempt to make it less complicated in order to remove the need for an option to actually do the negotiation. We just said you could unilaterally say, here's, you expose your timestamp resolution. And that was draft, I forget whose name was on it. It was draft somebody, draft Scheffenegger, TCPM, TS, something. No, that's the old draft. And there's the new draft. Bob was talking about the old draft. There's a new draft. So we already went down the negotiation rabbit hole, and we're like, this is really complicated. This is going to be a configuration thing anyway. I mean, in all of the use cases you're talking about, you own the entire configuration, right? So, actually, let me let you keep talking, and then I'll because I want to understand why you then are going back in a more complicated direction than the one that we did.
Sure.
Yeah.
And if you could also just email our team a pointer to the draft, that'd be great. Thank you. Yeah, so going back to the outdated parameters, so we've got TCP timestamps, delayed acts, the RFC, minimum RTO. They're all sort of interrelated, and it would be great if we could update them for today's data centers. And so the goal of this particular project is to take some code that we've been running internally at Google for all of our internal TCP traffic for many years, and the code basically allows us to negotiate some of these parameters and values, and we like to go ahead and release that as open source. But of course, because it involves an option negotiation, we'd like to standardize some agreement of what the option format is and what the semantics are, so that it makes sense as part of the open sourcing process. So we'd love to get people's feedback. All right, so next slide. So let's start with the minimum RTO. So most TCP stacks these days have a minimum RTO value that's somewhere between 200 milliseconds and a second. And there are a couple reasons for this, but two of the big reasons are, number one, that, as I mentioned, delayed acts are typically on the order of 200 milliseconds to 40 milliseconds. And so you want to make sure that you're allowing for that in some way. And then again, the RC minimum RTO is 1 second. But of course, in the real world, in today's data centers, the switches don't really have a second of buffering. And today, most hosts are sufficiently fast that it's pretty rare that the host itself is going to delay ACKs for that, that sort of time frame. So it'd be great if we could reduce the amount of time that we wait for any kind of timer-based loss recovery. In fact, TLP, RTO are the big ones, of course. So in Google's experience, over the past decade or more, we've found it very useful to use quicker retransmission timers, lower than 200 milliseconds. And other researchers looking at in-cast performance scenarios, and in the PDF you can follow those hyperlinks. They've also found that, of course, there's a big payoff if you just allow yourself to set smaller retransmission timers. And of course, the payoff can be easily on the order of 40x. So you can take what used to be 200 milliseconds for timer-based recovery and turn it into something that's around 5 milliseconds. And in fact, at Google, 5 milliseconds is the min RTO value that we've been using since 2013. And for many years before that, we used 20 milliseconds. And those both tend to work pretty well. And in fact, one of these research papers also mentions 5 milliseconds. So I suspect that we're not the only ones out there using 5 milliseconds. Sorry? Yeah, this is all for just internal traffic, yeah, between machines on Google's production network. Next slide, please. So, of course, if you allow yourself to retransmit packets after only 5 milliseconds, and then the receiver is still delaying ACKs by, say, 200 milliseconds, then of course you're going to set yourself up for potentially a much higher rate of spurious retransmissions, spurious reductions of your C-wind back to 1 packet, and of course that's going to be very costly in terms of performance. So ideally, you'd like to have some idea of how long to expect that the remote receiver is going to be delaying its ACKs in the worst case, so that you can try to avoid some of these spurious timeouts. And of course, one very simple way to do this is to negotiate this with the other end, obviously possibly in the handshake at the beginning of the connection. And so once you've negotiated some notion of the maximum ACK delay, here in the presentation I'm using MAD as an acronym, once you've negotiated some maximum ACK delay that allows you to use a smaller retransmission timeout, smaller TLP timeout, that kind of thing, then of course you can get some better performance. So that was the sort of first half of the show, which is delayed ACKs and min-RTO. So there's another part of this project that we'd also like to move forward with, which is microsecond timestamps. So in the TCP timestamps RFC, basically the finest allowed granularity is 1 millisecond. But again, that's 10x higher than the current 100 microsecond typical RTTs, and soon to be even further above the actual RTTs in data centers. So ideally, we'd like to have a finer grain timestamp. So what does that buy us? So one thing that's nice if you have finer grain timestamps is that you can make better use of timestamp-based undo, also known as the Eiffel algorithm. So the issue is that with the current RFC timestamps at 1 millisecond granularity in a data center environment, typically the original transmission of a packet and then the fast retransmit of that packet are going to happen in the same millisecond. So they'll have the same TCP timestamp. So when you get an ACK for that sequence range, you won't really know whether it's for the original or for the retransmit because they both happened in that same millisecond. On the other hand, if you have microsecond granularity timestamps, then with today's technology, you will actually be able to distinguish whether that was for the original or the retransmit in most cases. So you'll be able to undo any spurious recoveries that you did. So that's a nice feature, and it will be increasingly nice because one of the directions that people can go in data centers for higher performance is making use of multiple paths. But of course, if you've got traffic going over multiple paths through your switch fabric, there can be reordering, which can cause spurious fast retransmits. And so it'd be great to be able to very quickly undo those when when there wasn't actually a packet loss. So that's part one of benefits. The other benefit of microsecond granularity TCP timestamps is that it can allow you to do some nice, get some nice fine-grained measurements and diagnostics. And this is something that Van Jacobson on our team is particularly excited about. So if you have fine-grained timestamps, say microseconds, you can get some neat visibility into the one-way delay variation for both the data packets and the ACK packets, which can allow us to have a better understanding of the interesting congestion behavior you get in data centers, especially with incast, and potentially even maybe down the road use that for the congestion control. All right. So the issue is that, I mean, you would think it would be just a matter of just using microseconds in the timestamp value instead of milliseconds. It turns out to be just a little bit trickier than that. Because in the pause logic, there's actually a constant in there that has to do with a sort of tricky case. If you have a connection that's using TCP timestamps and it's using pause protection against wrapped sequence numbers, there's this issue where if a connection is idle for long enough, then actually the sender's TCP timestamps can wrap around, and you can have timestamp values that to the receiver look like they're in the past, when actually what's happened is that the connection's been idle long enough that the sender has actually wrapped its timestamp values. And it turns out, if you go through the math, that basically if you're using 1 millisecond TCP timestamps, that wrap happens after about 24 days. So in the timestamp RFC, it actually says there's that constant shows up, and it says basically, we're going to design the constants of the algorithm such that you can go down to one millisecond. So after 24 days of idle time, you need to basically just accept any timestamp value from the other side and consider it to be current. And so that's fine. That works out well. So if we dial down the granularity down to 1 microsecond, then the wraps can actually happen in 34 minutes, 1,000 times faster. So the issue is, if the sender is using microsecond timestamps, wraps 34 minutes later, if the receiver is using RFC constants, it's going to basically ignore and drop every single packet from that sender for the next 24 days until they can agree on what's acceptable. Sorry? Oh yeah. So it'll oscillate every 34 minutes. It'll oscillate between accepting things and not accepting things. Sorry about that. So that's not good. But obviously, one easy way to deal with that is just to negotiate that at some point, preferably in the handshake, so that both sides can agree upon how fast things are wrapping. So this handles the sort of general case where you're not sure what version of the TCP timestamps the other side is running. Obviously, if you do have a sort of closed environment, one administrative domain, and you're sure you've actually upgraded all your boxes and they're running the latest version of your TCP stack, obviously you don't need to negotiate, but you still want the parts of this code that allow you to use microseconds. Anyway, so we think it's worth having a feature where you can negotiate this. So, I have a quick comment. Yeah. So let's say,
thank you. So if we negotiate nanosecond timestamp, then we cannot use pause anymore because it's too much enough. 2 seconds wrapping time. It's far short compared to segment lifetime. So we cannot use.
For which one? For
nanosecond.
Oh yeah. So we're not actually advocating nanoseconds. Yeah, because that was just for illustration. I mean, if people, I guess we could put the bit in there in case, to try to future-proof things in case one day we do think that's reasonable. Since I guess we can sort of debate the value of pause in a world where everything should be encrypted anyway. But yeah, we're not advocating 1 nanosecond microseconds. We're just plugging for microsecond. Yeah.
Michael Wetzel, I have a very basic question about all these things here, which is I don't quite get why you need to negotiate. So what is the use case where you can't just configure both sides for instance, the RTO?
Well, if you have So if you, there are a couple of cases. So one is if you have a fleet where it's big enough that you can't upgrade everything instantaneously, which is most internet services. And then the other case would be if you have a cloud environment or a software as a service environment where you have some clients and servers and they're administrated by different people, but you want them to have high performance TCP traffic so that, you know, some customer can use your SQL server or your storage system or whatever. And
so you're proposing options as a way of bypassing the slowness of upgrades.
And to know when the upgrade has happened, so you don't get black holes if the other person happens to be running an older version of the protocol. Yeah, I mean we can debate whether it's worthwhile, but we think it is. Next slide, I guess. So, I mean, this is pretty straightforward, but just to give you a picture of the basic mechanism. So the idea would be that in the SYN, the active opener says, hey, the maximum I'm going to delay my ACKs is, say, 10 milliseconds, and can we please use microsecond timestamps? The passive opener records the maximum ACK delay advertised by the other guy, and then says, okay, I'd like to use microsecond timestamps too. So he sends back in the SYN-ACK, says, okay, I'm going to delay my ACKs by at most, say, 5 milliseconds. And yeah, let's go ahead and use microsecond timestamps. And then, you know, likewise on the other side, we record the other person's maximum ACK delay and the fact that we'd like to use microsecond timestamps. And that at a high level is how it works. Pretty straightforward, right? And then similarly, so how this plays out at RTO time. So on the sender, of course, you send a data packet, and then you're going to set some sort of timer, either TLP, RTO, something like that. Let's think about the RTO case. You're going to have an RTO value that's some function of the estimated round trip time and some function of the RTT variance. And then where before there had been a sort of fixed magical 200 millisecond slap value on most OSs, we're suggesting that we, when available, use this negotiated maximum ACK delay and budget for that on top of the RTT and the variance. And then on the receiver side, after we get the data packet, then we just want to make sure that we delay that ACK by no more than the amount that we've advertised that we would. Next slide. And then, so if we're going to negotiate this, this is one, you know, very straightforward way to encode this would be with a kind byte, a length byte. While this is experimental, it would need a 16-bit experiment ID. If it ever got to standard, obviously you could drop that. And then really you sort of just need 1 bit for microsecond timestamps. You know, if we wanted to try to future-proof it and allow for nanosecond timestamps, we could add another bit. And then we just need to encode the maximum amount that we are promising to delay our ACKs. And, you know, one easy way to encode that is with 10 bits for the value and then 2 bits to indicate whether it's milliseconds, microseconds, nanoseconds, or we don't want to negotiate it at all. And so in total, you've got 6 bytes here if there's an experimental ID, or 4 bytes if not. And so as far as current status, so we've been using essentially these 2 features at Google for all internal TCP traffic for many years. So for the maximum ACK delay, we've actually used that since 2005. And then for the microsecond timestamps, we used that for almost 2 years now. And we've actually heard verbal interest from at least one other major TCP stack for some sort of way to negotiate maximum ACK delays. And also, likewise, let us know if you're someone who implements TCP stacks and you have any interest in either of these, obviously. So as far as next steps, our team is planning on writing an internet draft and then changing our internal code to support an experimental option ID, and then sending the code upstream to the Linux community sometime by the end of Q1. And that's about it. We're looking for feedback of all kinds. Thank you.
My name is Martin Duke. I'm somewhat concerned about having the timestamp resolution inside this other option. if this option is rejected for whatever reason by the other host, then you'll have essentially an invalid timestamp option attached to it that could create problems.
So I guess if it's stripped or corrupted or something, I guess the negotiation would fail. I guess so. There's a detail that I left out of this super quick 15-minute presentation, which is that the way that we've implemented this internally so far is basically when someone proposes to open a connection with this, they send actually the microsecond value and the millisecond value in the timestamp option. They sort of take them, and so.
Well, can I propose an alternative?
Oh, sure, of course.
Rather than having one option influence the interpretation of an existing option,
Mm-hmm.
why not just create a separate option number that's identical to the current timestamp but is meant in microseconds?
Yeah.
Well, you could.
We're running out of space realistically.
Sure, of course. But second of all, you could just not use timestamp. But I think the issue is in that SYN, you've got essentially invalid. If the other host cannot interpret the new option, then you have a timestamp value that's not correct because you have to revert to the millisecond timestamps.
So if the negotiation doesn't work, which I think was the question, then basically the person who initiated the connection just assumes that it will, if they do go ahead and negotiate timestamps as being enabled, then we go ahead and we just use regular millisecond timestamps.
Do you want to come up, Tim? Okay. Hi, Brian Trammell. Again, I actually want to say everything's good, so I totally understand why you did this now.
Okay.
Actually, you fixed a fatal flaw in one of those two drafts that we talked about, so I'm not even going to send those to you.
Okay.
I want to come up here and reiterate a warning, though, in that, again, in the environment that you're using, the set of failure modes that you can get into is much smaller than the set of failure modes that you can get into in the internet.
Yeah.
And I really wish that I could come up here and point you to a generalized fallback for TCP options draft,
right.
but nobody's written it yet, and it's maybe kind of my fault.
Yeah.
But I would suggest maybe you look at how MPTCP did this, because they have sort of the same set of failure modes of, how can we actually know that we can start?
Right.
You have an option, a dependency between two options that complicates that a little bit, but some of the hard measurement and sort of heavy lifting and thinking has already been done by the MPTCP guys, so maybe you can steal some of that.
Right, that's a good point. Thank you.
Cool, thanks.
Jana Iyengar, I'd definitely be very curious to see the details of how the negotiation works out. On the MPTCP comment, I think it's slightly different because with MPTCP, you basically have a base level, which is that the TCP connection needs to be established. If the MPTCP option fails, you still have the TCP connection, and you go back to just being a plain old single path TCP connection. I think the failure modes are different here.
Mm-hmm. Yeah, and I guess we can also learn from the TFO case where there are options, and that might screw up the negotiation in terms of middle boxes dropping things. Yeah.
Any question? Well, I have actually naive one question. So how this will interact with rack? Because rack basically don't need precise timestamp in my understanding.
Right. Yeah, this is, I don't think there's necessarily an interaction with rack.
So right now it doesn't interact each other.
That's right.
Okay. Any other comments? Okay. Thank you, Neil. Michael? Okay. Wait 1 second. Yes.
All right, so this is an update on RFC 2140 bis. We presented that at the last meeting, and we were requested to do some updates and incorporated it. Next, please. So changes in this version are that we have added some more things to be shared. We've added TCP option state. In particular, this is about TFO, where TFO RFC already explains that you need to cache the TFO cookie as well as the failure to use TFO if it didn't work. And we generalized that to be sharing TCP option state. Then there is more discussion of problems related to sharing. That was brought up that the overall tone of the document is too positive, so we have made a little bit of a move in the more negative direction. Well, positive in the sense of suggesting to share. So I mean, this document can go in the direction of making very clear that you should not share certain things among flows, and you should share certain other things. Then there were some references that were brought to, suggested about SSH and RTT sharing related things that we have incorporated and we discuss. There is also a section in there about current implementation status, which we have extended with information about Windows, thanks to Praveen who sent it to us. Right, and we were asked to move TCP text, which is really old, from the old 2140 RFC to the appendix. Next. So this is the updated table. The blue line is this new thing, old TFO info. It's cached and shared in Linux and Windows. That's about the only thing that's cached and shared in Windows, together with the PMTU. Next. And yeah, so if this would be adopted, the work for the working group would be to discuss, how updates to the algorithms on how these variables are to be shared, specific TCP option details, because this is now just generally saying you want to share TCP options, and do's and don'ts for deployment. Next. At the last meeting, it was said that this should be informational, and I relatively quickly said, okay, fine with that, on behalf of all authors, when only I was there. So here I'm clarifying again. There are two possibilities if this should be adopted. It could be adopted as informational. That was the status of the original document. It was a non-working group document that was informational. Or it could be a BCP. The benefit of a BCP would be that it could make recommendations about things, and it could, if you, essentially what Joe has said is that if this document was to make recommendations regarding, for instance, not sharing certain things or being careful about SSH, then the status, according to him, should be BCP for that. I don't know. Personally, I have not much experience with BCP or informational status, so I'm just relaying that here. And that's it. So it's a request to adopt, and we'll see what you say.
Jana Iyengar, can you go back to the slide on what the variables are? Yeah, that one. Do you have any intuition about why it is that some variables are shared in some platforms and some not? For example, SSH is shared in Linux, but RTT isn't. And that seems very odd to me, but I'm not sure exactly why that is the case. In terms of making recommendations, this is basically documenting to some extent.
Yeah, because
it'd be interesting to actually know why it is that they do things that way.
I would suppose because people have found out problems with it.
Yucheng Chen, the way SSH is shared is that when the connection starts, basically if we have cached some SSH from the same destination before, then it's essentially set. So you don't start with the infinite SSH number, and you would exit a slow start based on whatever that's previously set.
Right. No, I understand that. My question was, why is something like RTT, which I would expect to be more stable, not cached?
RTT is cached. I think. Oh, actually, no. I noticed that. I think there might be a bug there that the ORTT is indeed cached and used in Linux in the connection initialization.
Okay.
Yeah.
That was my question.
Sorry. Okay, we can.
Yeah, I can happily point you the code that does that.
Yeah, we have like a longer internal list where we looked all the stuff up from the code. So this could be us taking it wrong from our own list. Or it could be something that we missed.
Personally, I think I have expressed some opinions on the list about this work, and I think after clarification that this is to document all the sort of update with all the new information that we have learned over the years, then I'm fine. My concern is that my personal experience about this cache, and also all the research paper I have read that talk about this is pretty much either negative or not that useful. So I think it would be interesting to put more discussion or analysis in the new draft, like why so far the result wasn't that promising. I think one key aspect is not just what data you cache, but at what granularity you cache. For Linux, it's based on the destination IP address, and that has known to be getting brittle, right? Like today, the same IP can be shared by 10 phones because the ISP are running out of IP address, and so they nap like hell. The other one is even on the same IP, let's say it's an IP shared by 20 devices at home, like my home, then it could be going through multiple different bottlenecks. Some could be Wi-Fi, some could be my TV that's directly connected to. So I think that's also worth some discussion there.
Okay.
Thank you.
Yushin, you like this draft as information or BCP?
Sorry, what's your question?
You like this draft as informational or as BCP?
To me, I think this should be informational.
Okay.
Yeah.
Ilpo Järvinen. I'm not fully sure what's the current status in Linux, but at least previously it used to be so that these values were cached only when the connection ended, which is not always that useful since you are likely to communicate with the same host within the same time frame, and then you go to some other host later. So also it might be useful to discuss about this, about when to actually store to this cache.
Okay.
Lars, so a long time ago I was Joe's student, so I know this stuff from back then. So I think Yushin makes a valid point, right? There are some fields in this table that are likely going to be okay, like MTU, right? Even if there's a lot of netting happening or something like that, or I don't understand how bad it is these days. But there are other ones that probably are more problematic. Right, and I wonder if we made two tables here, whether we could be a bit more. I'm blanking on my English this morning. Specific about what we want to recommend, right? Because right now basically says, this is how it is and this is how it should be. But maybe some of them, we are more okay with saying you can share, and others we say, well, today. There are probably issues if you do that.
I agree. I mean, yes. I think item by item, it differs.
Yeah, I think I agree with Lars. Breaking this into two buckets. One way to do that could be just. To me, actually, the cache is mostly useful on caching negative things because that could cause connection disruption or even complete block hole, like the fast open. Some device simply can take. If they see a SYN data, they will decide to stop forwarding your packet forever from now on, like some firewalls or security boxes. Those is actually very useful to cache in a positive way. But for things like C1, SSH, those are somewhat less, may not be as promising as you think that we remember the old array. Now, given the way that how the caching granularity is IP, maybe if we use different layers of information like HTTP cookies, or basically more fine grain with some kind of like a time variant, like time dimension that ELPO suggests. That might be more useful. But to me, it's the caching the negative information is the most useful part of the cache. Yeah.
Okay.
Okay, so there are several feedbacks. So maybe this is not adaptation call, of course, but I can try to send some feedback of this draft. So how many people read this draft? Not so many. Okay. Just one, two?
Two.
Okay. And then how many people think this is useful as informational draft? Okay. Around 10. Okay. How many people think this is useful as BCP? Okay. None. So I think my suggestion is you should update draft as more like an informational draft, and then we can think about if this is good enough to call for adaptation call. Does that make sense?
Yeah.
Jana Iyengar, it seems like the distinction that Lars was speaking about, saying these things are recommended versus these things we don't know about, starts sounding like a BCP more than an informational one. So we'd have to be clear about exactly which way we are going, I would say. If you're going to say that some things are useful,
yeah,
then that basically sounds like.
But can we make such?
I don't know. I have personal intuition and personal experience with this, but
that would be beneficial. But I'm not sure if we can or not. Maybe.
If we can.
Yeah, we can create solid recommendation, this kind of thing.
Lars, one thing you can do is you can do a BCP with an appendix that makes it very clear that the appendix is informational only, for example, if you wanted to split it that way. I wouldn't put it, so appendix and not section, because that's too easily confused, but an appendix after the references, right, that says like in big red, since we can do colors very soon, in text, informational only, that would work.
Okay, thank you.
Thanks so much. Okay, so we still have a time, so maybe this is the last presentation. Okay. So I need someone to. Marcel, please help. Thank you. Hello, my name is Yoshi, and I would like to talk about very small draft from me. So basically, I would like to talk about the increasing maximum window size. Next slide, please. So as you know, right now, the current maximum window size is 2 to 30th power order, and it's defined in RFC 7323. But if you look at the TCP max sequence number size, it's 2 to the 32nd order. So it's relatively big. So if we compare the max window size and then max sequence number, so max window size is almost 1/4 of max sequence number. So it seems to be a little conservative. That's the motivation of this draft. Next slide. Okay, so we have checked the logics in 7323. So in my understanding, if we have a 2 to the 30 bits orders of window size, basically when we receive the segment in 32-bit sequence space, we can exactly tell this sequence number is new, even from right edge of the window, even from left of the window. And then if we receive this sequence number, we can say, oh, this sequence number is old, even left edge of the window or right edge of the window. So this is the logic described in RFC 7323. Next slide. So now, suppose if we expand max window size 31-bit order, what will happen? So basically, there's something strange is happening here. It's when we see the sequence number, this sequence number looks new from right edge, but it all looks old from the left edge. So it's a little contradictory. But I think to know which segment is new or not old is not so important question to us, because the most important question is segment is inside window or not. Anything else. We don't need to know segment is old or new. It doesn't break any TCP semantics at all, as long as we know this sequence number is inside window. So move on to the next slide. So that's why we are trying to propose this idea. So let's increase maximum shift count inside window scale option. So use 15 as a maximum shift count. Right now it's 14, but let's increase to 15 because we believe it's safe. And then, so we update some draft, and then we, omit all signaling method and sync exchanging option things. We just send only updates logic. So send update, use new maximum shift count if they want. So you can, of course, you can update both sides at the same time, but you can update one side, but it doesn't hurt. There are some situations, it's create some performance degradation, but inside draft, we describe how to avoid such kind of performance degradation. Okay, go to the next slide. So, and then when I talk about this last IETF meeting at Yokohama, so many people think why this is important. I mean, it's just a minority things, but no, I might be maniac person, paranoid person, but that's who I am basically. So I think this can be beneficial for very long fat pipe, and that's one rationale. And then next reason is we sometimes see very similar question, why window scale size is 14, why we cannot do 15, it's too small. When from time to time, when I see this kind of question, it gives me some kind of heart burning feeling, why we cannot answer this kind of question properly. Because this is IETF, this is TCPM. So I think this is the place to provide answer such kind of question. I don't want to be very ambiguous on this point because this is TCPM. And go back. And then even if we extend sequence number space later, let's increase maximum in sequence number space 64-bit. But I think the same question still remains. We need to think about what's the maximum window size. It could be 30 bits, or it could be 62 bits. So we need to think about what's the right size of the maximum window size anyhow, eventually. So why not do it right now? And then also, I think TCP is to some extent kind of reference technology, has been, because it has been, exists for 30 years or something. So many people study TCP. So when some people design some kind of network protocol, and then when he has 32 sequence number space, so he might choose 30-bit max sequence window size, because this is what TCP does. But I don't know if this is the right thing or not. So my main motivation is to give us some conclusion if the window size shift count is 14 is right or not. That's the motivation. So go to the last slide. Okay. So any question? So some more detailed logic is described in that draft. So please read a comment and then provide the feedback to us. That's.
So as you're presenting, I just plug in some numbers. The current window scale value is good for about 50 gigabits per second over 100 millisecond link. And that's already including, you get enough receive window to even do one round of fast recovery. So I guess the question would be, do we expect that number to be challenged very soon, that TCP would over, say, a 100 millisecond link, right? A typical when we are expecting it to break 50 gigabits per second. And if we think so, I think this work would be worthy. Yeah.
We don't know how fast the technology has advanced.
So I take the answer as a yes. Will be soon challenging the 50 gigabits per second. Yeah.
I want to do it. At least me.
Yeah, Lars, I don't think it's going to be very soon, but this stuff has a long lead time usually before it actually gets deployed, and so it's not unreasonable to start this now, I think.
But no, I sometimes see this kind of question from people. I want to give answer to them.
Yeah, I think the answer is that there's a long lead time, and therefore it's a good time to start this now. If we might need it in 5 years, right? So the following question is: did I get that right? That we get a factor of 4? So we can not do we can't do 50 gig. We can do like 200 gig.
Yeah.
100. That's the max we're going to do ever. Okay. Because that's not that much more than what we can do now. So the question is: this is actually going to be enough for, it might give us a few more years, but eventually we're going to hit the hard limit.
Then it's okay to do it right now, right?
Yeah, I'm not arguing against doing it right now. I'm saying it's a good idea to do it right now. I'm wondering, so this might give us a little bit more time, but eventually we're going to hit the next limit, and then we better have quick.
Okay.
Yu-Cheng Chen, I think Lars is just arguing, if we are going to do it, do we just want to bump it by a factor of 2 or a factor of 4 or 8? Yeah.
Bob Briscoe, what I understood is you simply wanted to ask this question of how close it should be to the edge, whether it should be 4 times or 2 times. But I think in order to answer that question, we ought to be thinking about how we would increase the scale, because there are 2 possible ways. You can either sort of make all the fields 64-bit instead of 32-bit, or you can say that every reference to a byte actually means 4 bytes or 8 bytes or whatever, and scale it that way, and then make sure that all your TCP segments are a multiple of that. And so unless you know which way you're going to do that, you can't answer this question.
Stuart Cheshire, I was just thinking about Lars's comment about whether a factor of 2 is worth very much in computing. We like factors of 10 at least, right? We didn't upgrade from 10 megabit Ethernet to 20 megabit Ethernet. One thing I observe about this is it relies heavily on having the timestamp option, because without the timestamp option, it would be very easy for a slightly stale packet to appear to be in window. And if we're going to rely on the timestamp option, why not make the window 2 to the 32 bits? Make all sequence numbers be in the window, and then you rely on the timestamp to tell you whether it's old or new. That would give us a 4x improvement.
Okay, that's good. But one thing I want to say, this is very low-hanging fruit, so just increase the number. So very easy to do it. That's one advantage of this approach.
Jonathan Looney. I agree with the comment that we're relying heavily on the timestamp option, and that makes the alternate timestamp resolution proposals very important, because when if you had a nanosecond resolution, it's the window in which you can get a stale packet is very different, and a proposal like this is much more concerning the smaller the finer grain the timestamp resolution is. So it seems like to hit the high performance networking goals, we're going to have to extend some value, either 64-bit timestamps, 64-bit sequence numbers, something. Trying to hit higher targets with 32-bit numbers is going to be very hard.
Merkulevin, I would just be curious, do we have numbers what receive window values are used today? Because, I mean, this of course limits the transmission speed, but what it actually tells you is how much memory you have to have at the endpoints to
how much window size is actually used?
Yeah, what's the actual values you see on today's connections? Do we already go to the maximum? I would just be curious. It's not a question to you, basically. It's a question to somebody who has that data, I guess.
Lars, I can't give you a number, but we talked to some of the high energy physics guys, and they are still stuck in grid land where they need to use many, many connections in order to fill the really big pipes that they have between their sites. And they would really like to have, more standard transport. And but they're pushing a lot of bandwidth. But at the moment, they need a lot of connections because congestion control is limiting them, right? And that we're fixing that so they could go to fewer connections, but they're going to run at a much higher rate. And they do have 100 gig links between those sites, and CERN is generating an insane amount of data.
Okay, any more comments? Okay, as a chair, this work still need more time to think about.
Sorry, Martin Duke again. Has there been any experimentation on, I'm always harping on the middle boxes, on what happens if you set that field to 15? Is that being rejected by anybody?
Good point. I haven't tested it yet. On the receiver side, if it's received shift count 15, it's not automatically interpret as a 14. That's what RFC described. So even if you know the middle box modified value, it doesn't match that effect.
And Jana Iyengar, I was just pondering the point about the long lead times and Martin's point just now about middle boxes. Our lead times for changing anything in TCP are significantly high, not just a few years, but of the order of a decade. So if we want to actually try and change something here, I would go for the big one. Actually, let's go for 64-bit sequence numbers instead of trying to get an order of 2x or 4x improvements. That just seems like the sensible thing to try.
It may take time.
It all will, but the question is at the end of it, do you end up with a 4x improvement or a substantially higher one?
Okay, it's almost time. Okay, so we consume a 2.30-minute meeting. So thank you so much for attending, and then see you in Chicago. Where's blue sheet? Does everyone write your name on blue sheet? If not, please do it. Who has blue sheet? Blue sheet? Can you bring blue sheet to the chairs?
Yeah, well, so like for the bottom, so I have 5 networks we build. We sit in front of the hypercenters, the data centers of the world. So touch a lot of TCP traffic. We cache some stuff, we don't cache other stuff. Our operating system is called TMOS. Is that the kind of thing you want to cover in that draft, or is that just too much? I mean, you have to explain who the heck we are, because no one knows what TMOS is, right?
I mean, I don't know how widely used that is.
Well, just people that buy our boxes use it. But again, I mean, we have a pretty high market share on data centers. So I understand the tension